In this lesson, we'll go over solving trigonometric equations, and to start with, let's look at a very basic one. Where does sine of x equal 1/2? If you look at the unit circle, I actually know an exact solution to this. It's 30 degrees, and that's also the same thing as pi over 6 radians. So that's, like roughly right about here. This is pi over 6 radians, and that's where sine is equal to 1/2. Well, there's a second solution over here in the second quadrant. So we got this second one here that has the same y value as this point here. So again, we get another solution to this equation, but it's a different angle, and that angle is 5 pi over 6. That is if you go backwards pi over 6 from pi radians. I also included the graph of y equals sine of x here, because we can also see these solutions on this graph as well. Where does sine of x equal 1/2? Well, the y value of 1/2 is right here, and I see there's 2 places where sine is equal to 1/2, and that's really no surprise. I see there's a spot right there, and I see there is a spot right here. And these are the 2 solutions that I got from this unit circle, so I'm just going to label those. So here is, it's pi over 6, and this is 5 pi over 6. All right, are there any others? And the answer to this question is yes. In fact, there's infinitely many solutions to this equation. The reason for this is that the period of sine is 2 pi. That is, if you're at this point and you go 2 pi radians to the left, you find another spot where sine is equal to 1/2. So I'm going to label that right here. How would you figure out this angle? You would take pi over 6 and you would subtract 2 pi from it. So this is a new solution different from these two. And I can see it on the graph. It just is saying go 2 pi this way. You could do the same thing with this point. You could go 2 pi in this direction to get this solution. So I'll label that here. So that is, you would take 5 pi over 6 and you would subtract 2 pi. It doesn't show up very well in this picture, but, well, if subtracting 2 pi works, adding 2 pi will work as well. So you can also take those 2 initial points, so that was pi over 6, and you could add 2 pi to it. Or you could take 5 pi over 6 and add 2 pi to that as well. But you could do this process indefinitely. You could subtract 2 pi and then subtract another 2 pi. You could add 2 pi and then another 2 pi to both of these points. The idea is you can add and subtract multiples of 2 pi from these 2 angles to give you every single possible solution. This is how we would write that. We would write, if you want all the solutions, pi over 6 is one of them. But then you can add any multiple of 2 pi to it. So this is how we can express pi over 6 is a solution, but so is going to the left 2 pi and to the right 2 pi forever. Here n is an integer. So you could put -1 in place of this n if you wanted to go backwards 2 pi, or you could put +1 in place of n if you wanted to go forward 2 pi. Likewise, for 5 pi over 6, you can do the same exact thing. You can say, well, I can add or subtract multiples of 2 pi to this angle to get every single solution. So the answer turns out to be this. If you want every solution to this equation, well, I have pi over 6 and I have 5 pi over 6, but we actually get infinitely many solutions because you can add and subtract the period of the sine function over and over again. So this is the concise way to write it. There's technically infinitely many solutions, and it starts by finding 2 and going from there. So what about an equation that involves cosine and not the sine function? Will the same logic work? If I want to solve this equation, can I find 2 solutions and then just add or subtract multiples of 2 pi from them? And the answer is, yeah. The reason for this is the period of cosine is also 2 pi. So looking at this very basic equation, if cosine of x is equal to negative root 3 over 2, you have to start by knowing an exact solution to this equation. And okay, if I want cosine to be negative, that means I'm either in the second or the third quadrant. So that's like the place to start. It's got to be where an angle here or an angle here. I would start by thinking of, do you know an angle where cosine is equal to positive root 3 over 2? And the answer to that is, it's actually also pi over 6. So like, here's a 30-degree angle. Cosine is equal to positive root 3 over 2 at this angle. If you want cosine to be equal to negative root 3 over 2, you can find an angle over here. And just like last time, this angle is 5 pi over 6. So here's an angle where cosine is equal to negative root 3 over 2. If you want one more, because there certainly is another one down here, well, instead of going back pi over 6 to get to 5 pi over 6, we can go forward to 7 pi over 6. So these two angles are two solutions to this equation. There's a little bit more work to get there, but I started by finding an angle where cosine was equal to the positive of root 3 over 2. I then used facts I knew about the unit circle to get two angles where it was equal to the negative of root 3 over 2. Now, where does that show up within the graph of y equals cosine of x? So again, this is the function of cosine. Well, if you want cosine to equal a negative value, and it's going to be negative root 3 over 2, so it's like something right about, we'll say here, I see there's an angle here and an angle here. There's like two spots where that happens. So let's see, I have this spot and this spot. So some angle here and some angle here. What are those? Well, this one is 5 pi over 6, and this one is 7 pi over 6. So we have two solutions, 5 pi over 6 and 7 pi over 6. Is that every solution to this equation? And of course the answer is no. I see I can take this, go backwards 2 pi to get another solution right here. Likewise, you could take this one and subtract 2 pi from it to get this answer here. This graph continues forever in both directions, so you could just subtract another 2 pi, and then another 2 pi after that. You could also add 2 pi to get all of the points that are going in this direction. From what I saw on the last slide, to get every solution to this equation, I'm simply going to state, well, if I just add or subtract multiples of 2 pi to these two angles, it's simply going to give me this as the starting point and then move me back some multiple of 2 pi or move me forward some multiple of 2 pi. And so this thing here would be all of the solutions to the equation. And again, here, n is an integer. And even though here we're subtracting 2 pi, and this is a plus sign, the thing to point out is that when you say n is an integer, that means n could be, well, it could be positive 1, but it could also be negative 1. It could be positive 2 or negative 2. It could be 0. But if you let n equal to negative 1, that'll change this addition into subtraction, and so that's why you only actually have to use the plus sign when you're writing out all of the solutions. And lastly, well, what about tangent? That's the other trig function that we'll focus on for now. So like, where is tangent of x equal to 1? So over here I have the graph of tangent. Here I put in some vertical asymptotes at pi over 2, negative pi over 2, and so on. The period of the tangent function is not 2 pi. In fact, I'm going to state that the period is pi. Like if you go from negative pi over 2 to pi over 2, you've gone a distance of pi, and then the tangent function just continues to repeat. I don't think I need to use a unit circle for this question. I know an angle where tangent is equal to 1. that angle is pi over 4. That's where sine is equal to cosine. Where does that show up on this graph? Pi over 4 is halfway between 0 and pi over 2, and that's right here. So I'm going to label that spot. So here you go. This is a solution to the equation where tangent is equal to 1. Are there other solutions? And the answer is, yeah, there's infinitely many solutions to this equation. What you can note is, if you add pi, well, you get another solution, this one. If you subtract pi, well, then you get this solution here. In fact, you can add pi twice or subtract it twice. To get every single solution to this equation, what you can write is x is equal to pi over 4 plus any multiple of pi. So here n could be 0, 1, 2, 3, or 4, -1, -2, -3, -4, and so on. And these are all going to be solutions to this equation. So in general, this is the answer to the question. Now let's see if we can use these ideas to solve this trigonometric equation. Where is 2 cosine x plus root 2 equal to 0? The trick is, can you solve this thing for cosine and go from there? By that I mean, you can subtract the square root of 2 from both sides of your equation, and then you can divide both sides by 2, and you get negative root 2 over 2. So, this equation is equivalent to this one, but written this way, okay, I think I can figure out angles where this is a true statement. So I brought in a unit circle to try to help me figure out where, this could be true. For starters, I know where cosine of x is equal to positive root 2 over 2. That's here at pi over 4. So cosine at pi over 4, it's not negative root 2 over 2, but it's positive root 2 over 2. But once you know this, and the fact that cosine is negative in the second and the third quadrant, well, that gives you 2 other angles that you can use. The angle here would be 3 pi over 4, and also 5 pi over 4. So here are 2 angles. So, not this one, but this angle and this angle make this thing a true statement, and therefore they make this a true statement as well. So it's like, I guess, that's the solution. X is equal to 3 pi over 4, and also x is equal to 5 pi over 4. Of course, there's actually infinitely many solutions to this equation because you can add or subtract any multiple of 2 pi to either of these, and they will also be solutions to the equation. So technically, these are the solutions. There's infinitely many. They come from taking this angle and adding or subtracting any number multiple of 2 pi, and the same thing for 5 pi over 4. Let's try solving this trigonometric equation. So again, getting a little bit more complicated here. I think the approach will be the same. Like, get all of the signs on one side of the equation and move all of the numbers to the other side. So just to be a little bit more careful here, I think what I'm going to do first is subtract 4 sine of theta from both sides of my equation. And when I do that, I get 5 sine of theta minus 5 is equal to 0. And therefore, if I then add 5 to both sides of my equation, I get 5 sine of theta is equal to 5. And we can also divide both sides by 5. And that gives us that sine of theta is equal to 1. So this equation is more complicated, but it's equivalent to this much simpler equation. All right, so we want to solve this thing. Where is sine of theta equal to 1? Again, I think I'll have to bring in a unit circle to look at, but let's do that next. So here is the unit circle. Sine is going to be the y values, and there's actually only one angle. It's right here where sine takes on the value 1, and that angle is pi over 2. There are no others. This is the only one. So that means the solution to this equation is going to be theta is equal to pi over 2. But you could subtract 2 pi from this and end up at the same spot, or you could add 2 pi twice and end up at the same spot. Because of this, I'll just put plus 2 pi n, and this will represent all of the solutions to this equation. And the reason for that is the pi over 2 takes you to this point, and if you add or subtract multiples of 2 pi, you're still ending up at a place where sine is equal to 1. Let's change things slightly here in example 2. So we're still going to solve an equation, but we're going to put a restriction on where the variable can fall. Before it was just, it could be anything, and we got infinitely many solutions. But what if we say theta has to fall within this interval? And that means, well, it has to be bigger than or equal to 0, but also strictly less than 2 pi. If you add a restriction like this, there can't be infinitely many solutions to your equation anymore. So that's one thing that's different if you add in an interval. The second thing is, this isn't just sine of theta is equal to root 3 over 2, but it's sine of 2 theta is equal to root 3 over 2. How's that going to change things? This is my suggestion for dealing with a problem like this. It's just pretend that it's just like, sine of x is equal to root 3 over 2. And basically what I'm saying is we're letting 2 theta equal x. It's like we're making this substitution. We'll try to solve this equation and then go back to this to help us figure out the solution to this equation. So when is sine of x equal to root 3 over 2? When does that happen? Let's bring in a unit circle to help us figure that out. All right, so here's my unit circle. Sine is positive in the first and second quadrants. So the angle is going to be, well, one of them I know is going to be pi over 3. That's where sine is equal to positive root 3 over 2. But also here at 2 pi over 3. These two angles solve this equation. That is, the solutions are x is equal to pi over 3, but also x is equal to 2 pi over 3. But furthermore, you can add any multiple of 2 pi to this as well. So, these are all infinitely many of the solutions to this equation here. Okay, now let's go back a little bit. We weren't solving sine of x equaling root 3 over 2, but we're solving sine of 2 theta equals root 3 over 2. A quick way around this is to just replace x with 2 theta. So I'm just going to substitute it back in and say, well, this is the same thing as saying 2 theta is equal to pi over 3 plus 2 pi n. And 2 theta equals 2 pi over 3 plus 2 pi n. And because we're looking to solve for theta, and here we have 2 theta, well, you can divide 2 to both sides of your equations. So I'm just going to make a note that if you're solving for theta, what you need to do is divide both sides by 2. So if I divide this side by 2, I'll just be left with theta. And I have to divide pi over 3 by 2 and 2 pi n by 2. Pi over 3 divided by 2 puts a 2 into the denominator, and that gives me pi over 6. And if you divide 2 pi n by 2, it'll cancel this 2 and give you pi n. So here's one of the solutions for theta. It's really pi over 6 plus pi n. Same thing happens over here. If you divide 2 into this denominator, it'll cancel with that 2. So theta is equal to pi over 3. And then if you divide this by 2, the 2's cancel, and again, you're left with pi n. Okay, we're getting there. So the solutions to this equation are really coming from this stuff here. But here, this is infinitely many solutions. I don't want infinitely many solutions. I only want theta to be as small as 0 and as large as 2 pi. The next step is to figure out, well, what values of n are you allowed to use? Can you use 0? What about plus or minus 1? What about plus or minus 2? Basically, we just have to check, starting with 0 and then doing plus or minus 1, plus or minus 2, and so on, to see which of these values of n in these equations will keep me within this interval. And let's do that on the next slide. Okay, so these were the general solutions. There were infinitely many solutions, but we don't want infinitely many. We want angles that are only between 0 and 2 pi. So I'm going to start with what I think is probably the most obvious. I think n equals 0 will work. Because if you put 0 in place of this n, you're just left with pi over 6. And that's okay. Pi over 6 is definitely between 0 and 2 pi, so we're good. Likewise, if you put 0 here, you get theta is equal to pi over 3, and that's acceptable as well. I mean, these angles came from these equations, and they fall within this interval. I'll write it down, but I don't think we're going to be able to use like -1 or -2 and so on. The reason for this is if you try using -1, theta is equal to pi over 6 minus pi. And if you simplify this, let's see, that's pi over 6 minus 5 pi over 6. 6 pi over 6. That is -5 pi over 6. And it's no good. This does not fall within this interval. Therefore, I can't use n is equal to -1. It certainly is not going to work for this over here. If you take pi over 3 and subtract pi, you will not be within this interval. So it's like n equals 0 was our starting point. We got two angles that worked. Negative values of n will not work. So I'm going to try some other positive values of n. Like what about n is equal to 1? Will that work? Okay, my first equation, that is theta is equal to pi over 6 plus pi. If I simplify this, this is pi over 6 plus 6 pi over 6, and that is 7 pi over 6. And this is good. 7 pi over 6 is definitely less than 2 pi, so this is completely acceptable. Like these worked, and this one for n equals 1 works as well. Let's try it in the other equation. So over here, theta would be, that's pi over 3 plus pi. So theta is equal to, that's pi over 3 plus 3 pi over 3. That's theta is equal to 4 pi over 3. And 4 pi over 3 is definitely less than 2 pi, so that one is good too. In fact, you have to get to 6 pi over 3 before you actually get to 2 pi, so these are all good. Let's try n is equal to 2. Is this going to be okay? In my first equation, we have pi over 6 plus, okay, that's adding 2 pi. So theta is equal to, well, that's pi over 6 plus, that's 12 pi over 6. That's, oof, I don't think that's good. That's obviously not going to work, right? I mean, 13 pi over 6, that's too big. This is outside of this interval. And I think the same thing is going to happen with this equation too, without doing any work, right? If you do theta is equal to pi over 3, I mean, if you add 2 pi, I mean, you're already past 2 pi. I don't have to simplify this any further. I mean, that's not going to work. In fact, n equals 2 is no good. What does this mean? It means there's exactly 4 solutions to the original equation. Pi over 6, pi over 3, 7 pi over 6, and 4 pi over 3. I'll write all of those out, but they were, so we have pi over 6, that was good. Pi over 3, that was okay. So was 7 pi over 6, as well as 4 pi over 3. So instead of having infinitely many solutions, we had 4. So there's definitely some extra work to be done in a question that's where you're given an interval. You have to check to see, well, what values of n am I allowed to put into these equations? Figure them all out, and then get all of your solutions from that. Let's solve cosine of 4 theta equals -√3 over 2, but only for angles in the interval from 0 to 2 pi. So my strategy again is, well, let's just change things slightly and say, well, where's cosine of x equal to -√3 over 2? And, well, I know there's an angle where cosine is equal to positive √3 over 2. That's 30 degrees, or pi over 6. So this is where cosine is the positive √3 over 2. Therefore, if you want it to be the negative of this, we have to go to the second and the third quadrant. So that's going to be here and here. So my two angles are actually 5 pi over 6 and also 7 pi over 6. Therefore, all the values of x that solve this equation are the following. X could be equal to 5 pi over 6, but also you could add any multiple of 2 pi to that. Or x could be 7 pi over 6, and you could add any multiple of 2 pi to that as well. Of course, again, we were not solving for x, we were solving for 4 theta. So, just to make note, what I did back at the beginning is, instead of worrying about that 4 theta, I just called it x. I can now come down here and say, well, why don't we just put the 4 theta back and use that to solve for theta? So really, I want to see where 4 theta is equal to 5 pi over 6 plus 2 pi n, and where is 4 theta equal to 7 pi over 6 plus 2 pi n. What we're doing here is we're going to divide both sides of the equations by 4 so we can solve for theta. In the left here, if I divide both sides by 4, I get 5 pi over 24 plus pi n over 2. Because what we're doing is we're putting a 4 into this denominator, and I multiply that to get the 24. If I put a 4 in a denominator here, I have 2 over 4, which is 1 over 2. It'll be very similar to what we get over here. When I divide both sides by 4, I get theta is equal to, well, that's really 7 pi over 24 plus pi n over 2. The fact that these are becoming very small, and we're also adding small multiples of pi, I think we're going to have a lot of solutions to this equation. We're going to have to check the values of n that make theta fall within this interval. So again, what we're going to do is we're going to say, well, we have to check, n equals 0, maybe plus or minus 1, plus or minus 2, and so on. I think there's no way, we can let n equal -1 or -2. Like, the second you put a negative number here and here, we're going to be lower than 0. So I'm just going to start with 0 itself, and then check +1, +2, +3, and I'm going to see which of those angles leave me in the interval from 0 to 2 pi. So I'm going to start with n is equal to 0. I'm going to put them into these values for theta and just write down the theta that's left over. And this first one, theta, is obviously 5 pi over 24. And definitely that's good. It's positive, certainly less than 2 pi. Over here, if I put in 0 for n, I just get 7 pi over 24, and that is also acceptable. Okay, what about n is equal to 1? I think I'll do most of this computation on a calculator and just write down the answer I get to make sure we have enough room here. So theta is going to be equal to, okay, that's really 5 pi over 24, and I'm adding pi over 2 to that. Okay, and when I add those together, I get 17 pi over 24. That is certainly less than 2 pi. To be greater than 2 pi, this has to be 48. That did not happen, so this is good. Over here, I'm going to do the same thing. I'm putting 1 in place of this n, and I'm adding 7 pi over 24 to pi over 2. So 7 pi over 24 plus pi over 2. All right, when I do that, I get 19 pi over 24, also acceptable. Again, I'm waiting until I get to like a 48 or something that's bigger than 48. That's no good. Okay, so we're not there yet, so we're going to do n is equal to 2. If I put a 2 here, I'm just adding pi, so I'll do 5 pi over 24 plus pi, and then I'll do 7 pi over 24 plus pi. All right, so this time, all right, I get theta is equal to 29 pi over 24. That certainly is fine. Okay, if I do 7 pi over 24 plus pi, I get 31 pi over 24, also acceptable. Wow, we're still going here. Okay, n is equal to 3. Okay, well, what if I do 3/2 pi? Let's see what we get. So 5 pi over 24 plus 3 pi over 2. Okay, that is 41 We're getting close. 41 pi over 24. Over here, okay, if we do 7 pi over 24 plus 3 pi over 2, we get 43 pi over 24. I think we're at our maybe last stop. Let's see. What about n is equal to 4? Okay, so this is going to be 5 pi over 24 plus, yeah, this is not going to work. I'll just write it out, but if I add this up, I get 5 pi over 24 plus 2 pi. I mean, clearly we get, here 53 pi over 24. That's no good. I can't use that. It's too big. I certainly don't have to check the theta over here. It's only going to get bigger. So in terms of the solutions that we have, it turned out there were a lot of them for this equation. If there was no restriction, well, there would be infinitely many solutions. But because of this restriction, we could start at this 5 pi over 24, and we ended with this 43 pi over 24. And lastly here, I wanted to look at an equation that had tangent, but same idea. Tangent of theta over 2 is equal to 1. What are the solutions to this equation? And my starting thought process is, well, instead of worrying about the theta over 2, maybe I'll just call it x for the time being. And I really want to solve when tangent of x is equal to 1. I don't need to look at a unit circle for this. I mean, we already talked about an angle where this is true. That angle is pi over 4. And what's more is you could add any multiple of pi to that. But here, we're not solving for x. X was equal to theta over 2. And the thing we really want to solve for, though, is theta. So this is different because we have theta over 2. So I'm going to multiply both sides by 2 to get theta by itself. And when I do that, I have theta on the left. And if I multiply these two things by 2, I get 2 pi over 4. And that's the same thing as pi over 2. And then I have 2 pi n. So this is theta. I want all the values of n that make that theta fall within this interval from 0 to 2 pi. So which values of n are we allowed to use? Like last time, we can't use a negative number, so I have to start with n is equal to 0. When I use n is equal to 0, I get theta is equal to pi over 2. So that's good. I can use that. Well, what about n is equal to 1? Okay, this is going to be theta is equal to pi over 2 plus 2 pi. That's a problem. That's too big. And because of this, I can't use this angle. In fact, there is only one solution to this equation. Theta is equal to pi over 2. Any other angle you use will not fall within this interval.